All right, so thanks again, everyone, for joining. Welcome. My name is Felipe. I'm so happy to see many of you having some level of interest in learning a bit more about Rust and also a bit more about ScyllaDB. And I'm your host for today's webinar, Single Mains Army. So things real quick you should know about me. I love puppies, so you guys basically are obligated to like me. Second, I am one of the co-authors for Database Performance at Scale, a free book published by ScyllaDB. And I am also a ScyllaDB committer, so I also contributed a tiny little bit with ScyllaDB's code base. So I work as a technical director at ScyllaDB, and for those of you who are not familiar with it yet, we are the database for organizations requiring predictable performance at scale. ScyllaDB was built with a close-to-the-metal design that squeezes every possible ounce of performance out of modern infrastructure. This translates to predictable low latencies, high throughputs, and ultimately infrastructure savings. We are available both as a managed cloud offering via ScyllaDB Cloud and also as an enterprise offering. And since ScyllaDB is a NoSQL database, we also provide full compatibility with both Apache Cassandra and Amazon DynamoDB APIs. So here's a short list of logos currently using ScyllaDB to support their data-intensive workloads. Blue Sky, for example, has been getting lots of attention recently as a microblogging social network. In fact, even yesterday, one of their backend engineers, Jazz, posted a blog about ScyllaDB. Well, not about ScyllaDB, they mentioned ScyllaDB. Hulu and Disney Plus are also use ScyllaDB as part of media streaming. And yes, great blog post. TripAdvisor and Tubi use ScyllaDB for machine learning recommendations and so on. Discord here at the bottom, guys, and very related to our topic here today, is a great example of a company using ScyllaDB and Rust heavily in their backend to support their users' real-time messaging experience. So you may definitely want to also check out some great blogs Discord has wrote on how and why they are using Rust. All right. So, okay, let's take a quick look at our agenda items, which I put together for us to discuss today. First, let's start with some background over why we are here today, what makes Rust so special, what is Tokio, and what is the relation it has with ScyllaDB, if any. Next, we will do a quick app walkthrough to understand what we'll be covering here today. Of course, just like most applications out there, our app will need to connect to a database. And since you are in a ScyllaDB provided webinar, we are going to connect with ScyllaDB using the ScyllaDB Rust driver. And lastly, we are going to run this app, and as time permits, walk through the code to understand what it does under the hood. All right? So, folks, this is not mandatory, but I added here a slide in case you want to follow along. And the main reason is because, developers often like trying things on their own, and setting things up can take some time, to pull containers, build or necessary images, etc. and so forth. One heads up I have for you is if you're using Linux, ensure that you install Docker, not the one supplied by your OS distribution. And because basically the Docker Compose, which is provided in the GitHub repo above, is basically not compatible with old Docker dash Compose implementations. But everything is explained in the README. All right. Cool. So at this point, it's important for me, at least, to provide you guys with some context over the question, why Rust? Rather than Java, Go, or other languages. Why aren't we talking here about Python? After all, it is definitely a programming language that gained lots of popularity and attention recently. And this is primarily due to its high performance and efficient use of system resources. Rust makes it very easier for developers to build highly concurrent asynchronous applications with special focus on memory safety, which is really the dream of software engineers out there. Uh, in particular, not having to worry about things like garbage collection pauses. Someone mentioned about Cassandra and wishing turns Java, null pointer exceptions and dereferences, memory leaks, and other things really differentiate Rust compared to other languages. So if you are starting your Rust journey, I highly encourage you to start with the official Rust book available in the official Rust website, and then build up from there. And one thing that you should know when you start coding with Rust is that the path is not really as straightforward, but in general, and you are probably going to hear this from many Rust developers out there, is that learning Rust will make you a better programmer in the long run. And when we talk about data-intensive applications, those applications often rely on asynchronous programming to quickly process lots of data. In the Rust world, this means using the Tokio framework, which facilitates the task of never blocking while waiting for resources when you need to fetch some data on disk, on the network, etc. All these characteristics really make Rust a good fit for, saving on infrastructure costs or making better use of your limited resources, as is the case, for example, if you are working with embedded IoT devices, for example. More often than not, you will be using Rust to build scalable backend applications, and inevitably, you will need to communicate with a database to store and retrieve data as needed. And this is really where ScyllaDB fits in. We are the only database geared for extremely high throughput while sustaining single-digit millisecond latencies. Compared to Rust's Tokio, in ScyllaDB, we make use of another framework, and this framework is called Seastar. Seastar is an asynchronous C++ runtime following a polling architecture. Requests or futures are submitted for processing shortly after they arrive, and then the Seastar reactor, which runs in a busy loop, waits for the resulting promises to actually complete. So although ScyllaDB uses Seastar, so that's something you should be aware of. ScyllaDB is not written in Rust. We do have components in ScyllaDB that make use of Rust, but our core database is basically written in C++. So although ScyllaDB uses Seastar, it's worth mentioning that other projects similarly make use of Seastar as well. A few examples are Red Panda, which is like the C++ version of Kafka, very fast. And the Ceph distributed storage system also has one integration which make uses of Seastar for handling high I/O throughput. So what makes Seastar different than Rust, Tokio, and other frameworks? There are basically two main things that differentiate Seastar. First, we follow a concept known as shard per core. Shard per core means that incoming work gets sharded on a per CPU basis. And every CPU that you have in your virtual machine, in your hardware, runs its own dedicated reactor loop. It also means that the architecture follows a shared knotting model, where each CPU gets assigned its own portion of memory and disk I/O. And because of that, no context switches exist. This is important because one thing that's very detrimental to performance is context switching. This can greatly reduce your performance, which often happens when you are working with threaded applications. Furthermore, cross-CPU communication and synchronization in ScyllaDB and in Seastar do not rely on any locking primitives. Instead, it is simply implemented as an asynchronous messaging passing. The second aspect about Seastar drills down its user space schedulers, which is pretty much depicted here on the right-hand side. Um, Data-intensive applications, as you guys know, and as the name suggests, they can be very intensive. And because of that, it is important that the database efficiently makes a use of your I/O resources in a smart way to maximize its utilization, while also being able to carry out other background tasks. So the Seastar I/O scheduler abstracts away from programmers and dynamically tune task priorities, which you're defining your application, as the workload conditions vary over time, while providing all the goodies in asynchronous and as direct I/O can provide. So one example about our user space I/O scheduler, since we are a database, if you are familiar with Cassandra, for example, you know that Cassandra has this process known as compaction. ScyllaDB has compactions too. So one of the things that we do is if the system is actually running under very little load, we basically speed up the speed of compactions. So because we have additional resources. And then when the user workload is actually requiring lots of traffic, we dynamically adjust the priority so that compactions will basically consume less IOPS and bandwidth. All right, so this is one example on how basically our user space IO scheduler works. All right, so we are about to dive in the Rustation word, but before we do, I want to ask you folks, how proficient are you guys currently with Rust? There's one option here called like Felipe, I'm learning, and I would like to know the individual who actually added this bullet option. But I believe it makes sense, right? Life is always a learning curve, I guess. But I think we have run this poll, now being serious, I think we have run this poll about 3 or 4 times already, and I always get impressed on how the responses vary over time. So yeah, please do let us know how proficient you feel about Rust. And with that, thank you so much, folks, for your responses. So after all this introduction, let's discuss the simple app we are going to walk you through today. So this app is basically a 3-part component where first we are going to learn how to ingest some data to ScyllaDB. It deploys our initial schema, and then it's going to simulate an IoT application, basically generating measurements for a while. Quite simple. Next, the second program, metric reader, the one at the middle, is basically an aggregator. And this is more of a complicated program. It basically what it will do is what we call as an efficient full table scan. So it will basically scan through all the data we ingested and allow us to run analytic queries and then infer things like how many measurements each device recorded and what was the maximum temperature and so forth. And lastly, we are going to run the third and final program, which is arguably the most straightforward one, to demonstrate how to run point queries and retrieve a specific device maximum, average, minimum over a specific period of time. All right. So in order to do all that, naturally, we are going to need a driver, right? And with regards to the Rust support, you can feel rest assured that this is another area where ScyllaDB shines. We are one of the few database vendors out there that actually ships with a native Rust implementation. And in general, when I am working with Rust and I'm trying to integrate it with other systems, not always you are going to find native implementation. And makes me a bit sad sometimes because I believe Rust is really an awesome language. So having a native Rust implementation definitely makes a difference. And remember what I previously mentioned that ScyllaDB is compatible with Apache Cassandra. So what we did was to compare the performance of our driver versus the GoSQL driver, as well as the Cassandra Rust driver. And well, despite its name, the Cassandra Rust driver is not really a native implementation. What the Cassandra Rust driver it basically relies on the C++ driver API to basically translate syscalls and then convert the types, from C++ to Rust. Um, so as we can see in the results, our native implementation is around 3 times faster than GoSQL, where the C++ implementation, the C++ bindings to Rust, is just super slow. So another cool thing about behind developing your code in Rust is basically the ability to, you make use of Rust bindings. And Rust bindings allow you to easily reuse and share a given library feature in Rust to other languages. And this is done via foreign function interfaces as available in most major programming languages. And this is exactly what we have done with our C++ Rust driver implementation, which allows you to benefit from Rust performance when you are coding C++. And likewise, we also have community members who created the ScyllaPy on the right-hand side, which does the same, but for the Python language. So think about, as a developer, about the benefits that this approach can help you with your code base. One benefit that we see here at ScyllaDB is that we no longer need to maintain separate driver implementations on a per language basis. As the Rust driver is used under the hood, shipping new features or fixing bugs automatically extend its benefits to its children implementations. Therefore, I definitely look forward to a foreseeable future when you are using Rust without even knowing it. And I really like that we are seeing lots of traction in the chat. So, all right. So we already know that we want the ScyllaDB Rust driver, and likewise, in your real life, you may be after a given library that exists. So how do we go about it, considering you are learning Rust for your first steps with Rust? On the right-hand side of this slide, there's a picture called of crates.io, which is like PyPy or NPM.js for you to, easily find and learn how to bundle specific libraries in your code. In our example, we are showing the Scylla crate, which is, and a crate, for those of you not familiar with the Rust vernacular, a crate is basically analogous to a library or a project. And one particular thing about crates is that crates provide features. And by default, features are additive. So when you enable a feature, it adds some functionality to a given library. For example, in the example shown on the screen, we can see that the Scylla crate has an SSL feature for enabling encryption in transit. So when your application is communicating with your database, you enable the SSL feature, and then this feature is going to compile all the OpenSSL dependencies, and then you will be able to communicate with your database in an encrypted way. We also have other features like cloud, which is to be enabled when you want to connect with our ScyllaDB cloud offering. And we also have other features related to types conversion and serializations. So why can't we simply enable all features? Well, you can, but having features you don't need disabled help, with reducing your binaries bloat, which in turn enable you to basically have faster compile times. Smaller binaries often help with disk space utilization, and more often than not, your application bootstrap times also improve. So those are a few reasons why typically you don't want to enable all features, but on a per need basis. All right. All right. So enough context, enough talking about fundamentals, yada yada. So let's run our programs now and actually see what they do. So allow me to switch to my terminal. If my font size is too small, do let me know. I can easily zoom that in. So in case you guys, for whatever reason, decided to follow along, this is basically what you will want to do. You will start Rust, you will start our project using Docker Compose, and this is going to start 3-node ScyllaDB cluster, and then our Rust application running in a separate container. Okay. How do I know when I am ready to start? So one of the things I did when I built all this was basically I added on the logs of our Rust application this message. Okay. So basically our Rust application starts and then it keeps checking whether ScyllaDB has fully started. So if you see this message that ScyllaDB is up and available, well, you're ready to go. All right. So once that's done, the next step you want to do is basically logging to, well, get a shell on your Rust app. And then here, you are basically going to see all the three apps we spoke about. Metric collector, the one which basically ingests data. Metric reader, which is going to scan the data we ingested. And then UUID finder for running basically point queries. Okay, so let's start with the first one because this first one basically creates our schema. So what I'm going to do is use cargo, and cargo is typically the main command line you are going to use, to compile things, to build binaries, etc., and so forth, as you go with Rust. The binary I want to run is metric collector, and then I'm going to specify my contact points. Everything is on the README file on the GitHub repo. Data center 1. And I guess that's it. Yeah. And boom, just like that. So it took me longer to actually run the command than for the driver and the database to actually acknowledge 86,000 operations per second. And remember, all this is running on my laptop. If we take a look into the latency, again, this is running on my laptop. It wasn't actually that bad. So basically what we did here, just as a reminder, we inserted the data for 100 devices. And if I recall correctly, if I remember correctly, the amount of data for 2 days. All right. So let's say now, let me switch to my VS Code so we can actually see what is the code doing under the hood, right? So that's our cargo.toml file where basically we define, the structure of our project. And if you go inside our metric collector, you will see another cargo.toml file where you're going to see all the dependencies which our project uses. Here is basically the Scylla driver being referenced to the version we use. And you are going to see that we are making use of this feature called Chrono. And Chrono is needed so we can handle Rust, date time, or Chrono conversions to SQL types. All right. So if we look at the code, basically you guys are going to see that I added everything under a single file. And you may probably and correctly say, hey, this is not a good practice, right? Yes. I like typically when I'm demonstrating things to have all the logic I need under a single file because I find it easier for us to follow along. Imagine trying to figure out the structure of a project, etc. We waste too much time on that. So that's basically everything you need to know, single file, 200 lines, and that's it. So what do we do here? Basically, we define some constants, which are basically how many days we want to load the data. And you can play with those values on your own. So you can see how the database sustains traffic over time, uh, uh, um, how is the latency, how is the latency at the different concurrency levels, etc., and so forth. So you can simply change those as you better see fit. And then what we do next is basically we parse the initial command line parameters. And I do it in a very naive way. There are libraries in Rust, things to parse command line arguments, but I decided, no, I am not going to make it this complicated. It's just get a string and assign it to a variable, very simple. And then we define the key space and the table we are going to ingest our data. So someone is saying that they're having trouble bringing up the container. The error message you are seeing pull overlaps with another one in this address space means you have probably another Docker network created which overlaps. So you have to delete the other Docker network you have, then you use or change the Docker compose file. All right, moving on. We define the key space and table we are going to use. For those not familiar with key spaces, this is a Cassandra originated terminology. Imagine a key space as a database in the relational world. Basically, inside a database, you create tables. Okay? And then table is pretty much self-explanatory. All right, so what's the first thing we do? What's the first thing we do after we define all our initial variables? Well, first thing is we define the policy we are going to use in order to connect to the nodes in our cluster. There's a lot of information here. So one of the things we define, for example, is that we want all of our queries to be confined only to nodes in a specific data center. So ScyllaDB is basically a distributed, highly available database, and you can have nodes across multiple data centers, multiple regions. So the trade-off typically is if you were to route queries to a remote and distant region, you would pay the price in networking latency. So because of that, we prefer a single data center, which in our case, since everything is running our laptop, doesn't matter, but I added here just for you guys to learn how to use and integrate it with ScyllaDB features. Token aware, what is this? Token aware is basically a load balancing policy, which means that queries are always going to be routed to nodes which hold on the data that you are basically querying. So for example, if you have, I don't know, 12 node cluster, and you only replicate your data to 3 nodes, then a query to a particular partition is effectively going to be routed only to 3 replicas. All right, so this is what token awareness is, and it helps with reducing latencies. So after we define our policy, we then create a profile. And this is a very nice thing that the Rust driver provides. If you are a Python programmer and you are familiar with the Cassandra or ScyllaDB Python drivers, you will probably recognize this. So a profile basically allows you, to create different policies and load balancing policies on a per use case basis. So sometimes you may want to run queries which require very low latency, and sometimes you want to run queries which are heavier. So if you want to specify different connection parameters, you can specify different profiles and then route your queries using different profiles as you define it in your application upfront. All right. Then after all that's done, finally, we connect to the cluster. All right. We use compression because our data set is pretty much It's a timestamp, it's a with, and a few floating point numbers. So it's very small. So it's a highly compressible data set, which is important because networking traffic can get quite intensive, especially if you're running the cloud, AWS, GCP, you typically pay for cross availability zone costs. So compression your data is typically a good thing. And then we specify the user and password to connect to the cluster here. And yeah, that's it. We connect to the cluster. Uh, the next steps which follows are basically creating our database resources. So we create the key space here. So that's how basically you run a query using our Rust driver. You basically get the session we created earlier, dot query, and then that's it, done. And then after we create the tables, so it's very straightforward. And then what we do next is we basically prepare the statement. We use prepare statements in order to run our next ingestion queries. So for example, we are defining that we want to disinsert statement, which is going to receive three bind variables. So whenever we execute that statement, we expect the application to always provide three bind variables. And then we prepare the statement, and then we define this prepared statement with a consistency of local quorum. So there are obvious reasons why you should always prepare your statements for any database. This prevents things like SQL injection. It's a bit odd that we are in 2025 talking about SQL injection, but yeah. And another good thing about prepare statements is that it helps your database with saving important CPU cycles. So it's even better for latencies at the end. We then define a retry policy. We use the default retry policy. So this is kind of a no-op statement. If you did not set it, it would have the same effect. But this is just in case you want to change the retry policy you are using. So that's how you would basically specify your own retry policy. Okay, so after we defined all this, that's effectively when we are going to start using Tokio to basically, send the queries asynchronously and concurrently against our database. How we do that? I don't know. Someone said in the chat that Rust can easily overwhelm the network, and that's true. And if you do not take care of controlling your application concurrency, likewise, you probably can also overwhelm your database fairly easily. That's the power of Rust. So what we do here is at the beginning of our code, we define this parallel constant. And what we do is we spawn a semaphore, allowing at most just the number of queries being running in flight at a given point in time. So I'm not sure if you are all familiar with the concept of semaphores, but basically you get a permit, and then this permit is eventually released after the code completes. That's how it works. And then we specify how many devices we want to ingest, and then we looping in a synchronous fashion and start ingesting data asynchronously and concurrently. All right. So this is here is basically the section where we basically we use Tokio to spawn our Tokio tasks. And we start basically, the only thing we do really is execute the queries we want. And because we are controlling the concurrency via a semaphore, we ensure that we do not overwhelm the database. All right. So after everything is done, and this is important when you are doing synchronous programming, we wait for all the in-flight requests to finish. And then after our requests basically complete, then we print the final metrics back on the screen. And this is the quick, well, it was a bit lengthy walkthrough over our first step. But the next ones are going to be simpler because you are going to see again pretty much lots of the things we already discussed. All right, so that was the first step. Let's now see the second one, which is basically that one which remember I told you was a bit more complicated. So the second one is basically called metric reader. And we are going again to specify our contact point and our data center. And what the metric reader program does basically is it runs what we call as a full table scan. And this requires a bit of an explanation. So let's actually look into its code and only focus on what it has different compared to others. So basically, what we do in this code, the metric reader, is basically we define how many nodes we are working with and how many cores, how many CPUs each node has. After we assign those numbers, we basically define our concurrency. This should be the name of this, actually, it's concurrency, not parallelism. We basically define how many concurrent queries we want always in flight. And we basically add a times 3 factor here because we want to ensure that our ScyllaDB CPUs are always busy. They are never idle waiting for a request to arrive. So what happens effectively is, depending on which value you set here, depending on the factor you set here, you are effectively going to allow your application to send more requests concurrently against your database. As long as your latencies are good, you can keep on increasing. But eventually, one thing you are going to see is that you are going to observe that your latency is actually going to get very high and your throughput is going to deteriorate. So balancing the right concurrency is often a very delicate balancing act. But I added here the code in case you want to play with it later on your own time. Why it's 3 and not 4, 5? It could have been 5. That's a great question, actually. Basically because we always want a concurrency of 3 queries at least to be hitting each one of our CPUs on every single node that we have assigned to our cluster. That's why it's 3. If you want 5, you simply change the number to 5. All right? What else we do in this code particularly? One of the things we do is we divide the token ring, which is basically how a ScyllaDB cluster is actually observed. We divide it in very small chunks. So a token ring is basically, by definition, a very large range, a very large number, which means that if you do not do this division, each query you run here concurrently would potentially read and have to add too much overhead to each single node you have in your distributed cluster. Because of that, you typically want to split your work in a divide and conquer approach, such that you can basically benefit from your distributed infrastructure, such that your work completes faster. So for example, if we had this value set to 1, as you can imagine, we would run only one query. We would effectively only run our concurrent, the value of our concurrency number of queries. And this is typically not good. Imagine if you have to scan 1 terabyte of data. If you split 1 terabyte into 3 nodes, 2 cores times 3, it's going to be a very large number, right? So that's why you typically want to split each query into smaller fragments such that you concurrently can benefit from your server speed. And again, the right number here the right number of splits is pretty much going to depend on your use case. All right. So this is pretty much what we do differently here. All the rest of the code is pretty much simple. Here is where again we spawn Tokio, and then you guys can learn more about the underlying code at your own time. Okay. And finally, let's run our last program. And this one I'm going to cheat, guys, because it's lots of things to type. So I'm simply going to copy and paste, if you guys don't mind. And this is very simple, really. It's basically how you would use the driver to run a point query against ScyllaDB. So basically, we specify the device you want to retrieve data, and then we run things like retrieving the maximum, minimum, and average temperature recorded. And by the way, in case you are wondering how was the max 49 and the minimum 39, basically we generated the numbers randomly, okay? So you can tune that if for whatever reason that annoys you. Yeah, I think this program is very, very straightforward. So with how we have discussed it already about Rust and the driver, you can pretty much get to the gist of it once you check its source code. All right. So this is pretty much what I wanted to share with regards to Rust coding. Let's wrap up. Thank you so much for joining us today. If you'd like to learn more about ScyllaDB, please follow us in our social media. We are always generating fresh new content, benchmarks, comparisons, interesting content like this, Rust. We love investing in the Rust world. Follow our GitHub, Twitter, Blue Sky, Slack, LinkedIn, etc., and so forth. And I hope to see you guys next time. All right. See ya. Bye.